right now,
Uh-oh.
says YouTube.
Uh-oh.
An error occurred. What? I'll bet you it's working.
It's working.
Yeah.
Maybe you could try unplugging it and plugging it back in.
Yeah, YouTube. That's weird. All right. Yeah, that's never happened before. Okay, people are telling me that the wave function has collapsed, that we exist. We've instantiated, we've chosen this universe to exist in, and not the countless other universes. Now's your chance to say hello. So this is the ultimate episode, not the penultimate, which I'm so happy to say every week. This is it. This is the end for this season. So we are going to be posting a really cool clip that we did from the Weekly Space Hangout about 3 weeks ago. They're on my YouTube channel, and we've gone and made it all fancy. So there was this segment where Brian was talking about masers used to calculate the as another method of calculating the cosmological constant. And it was really fascinating, and all of the various co-hosts did a great job. And so we thought it was so interesting and covered a chunk of that we missed on my channel. And so we just took the whole thing and then just put a pile of really cool graphics and stuff to it to make it nicer. And then we're going to be releasing that Friday. And hopefully that'll bring a lot of new subscribers to the Weekly Space Hangout, who then won't be able to watch the show because it won't be back until September. But still, I thought it was a lot of fun, pretty fascinating conversation. So you'll see that in a couple of days. Yeah, happy Canada Day, everybody. We celebrated like crazy today. I didn't celebrate. We're very low-key about our national holiday. What did I do? I went to the store and bought some soaker hoses for the garden. Hello to Adam Synergy, Alex Displand, Andrew Planet, Andy Cowley, Brexit Denier, David Dunn, David Fairweather, Horizon Brave, Ian Farquharan, J. Alex Anderson, John Musk, Johnny J, Johnny Zed, Larry King, Luke Duke, Nancy Graziano, Ocean McIntyre, Powell Zersky, Rich Wilson, Arjone, Topes, Zappan. Hey, everybody. How you feeling, Nancy Graziano? Are you ready to take a 2-month break from doing all of this executive production that you've been doing? Thank you, Nancy, for all of the work that you've done this year. You've been incredible. There's no way this show would exist without you at this point. And we really appreciate all of the work that you've been doing. So have a much needed holiday like the rest of us. We'll go one more minute and then we'll get started. Everybody's so quiet, so focused. Look at them. They're all just like coiled springs of science.
We're all sad that this is our last one.
I know.
We have to wait until September.
This is it. Okay, let's get started. Put you all back in your boxes. Back to me. And here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, July 1st, 2020. Happy Canada Day, everybody. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about the Mars landing site, quasars, extremely active in the early universe. Finally, we understand why Betelgeuse was dimming and a star that just disappeared. Joining me this week on my screen, I got Michael Roderick. Michael, welcome back.
Hello. Thank you for having me.
We've got Carolyn Collins-Peterson, the space writer. Carolyn.
Hi there. How you doing?
What's your background? That's cool.
It's Mars.
Right on. Let's see. We've got Beth Johnson. Beth.
Hey, Fraser.
Welcome back. And you also have Mars.
I am also on Mars.
Right on. All right. Before we get on with this week's show, I want to remind everybody that one, this is the last episode of this season of the 2019-2020 season. We're now about to go on our 2-month hiatus for July and August. But you should take this time and go and join the Weekly Space Hangout crew. This is the fans, the community, and they actually formed in the first place many years ago because of this hiatus. There was a bunch of fans. They wanted to stay in touch with each other and be able to share interesting space news and keep themselves sane during the long drought over the summer while they waited for the space news to return. And the crew's been going strong for years and years and years. So if you want to be a part of this amazing community, help plan out what the show is going to do next season, take action. Go to wshcrew.space. They will give you your executive producer privileges. Then you can decide which guests are going to be showing up in the fall season. Do it. wshcrew.space. And I just want to give a huge thank you to everybody in the crew for all of your hard work over the year. This show literally, and I mean this from the bottom of my heart, would not exist without you. We do this with you and we do this for you. And it's an absolute honor to work with you every week. Now, let's get on with our special guest. This week, we've got Andrew Simeon from the SETI Institute and other places. Andrew, welcome to the Weekly Space Hangout.
Thank you for having me. I feel very privileged to be here on the ultimate episode.
On the ultimate episode, yeah, exactly. So who are you? What do you do?
Well, I'm an astronomer, and my principal research interest is the search for extraterrestrial intelligence. I'm jointly affiliated with the University of California at Berkeley, where I direct the Berkeley SETI Research Center, and also the SETI Institute, just a bit south of Berkeley in Mountain View, where I hold the Bernard M. Oliver Chair for SETI.
Now you actually, so you've got sort of two hats that you wear. There's the work you do with the SETI Institute and the work you do with Berkeley, but it's all falls in the SETI world. And of course, you are influential on Breakthrough Listen, which we have talked about quite a bit in the past. But can you give people an overview of what Breakthrough Listen is trying to do?
Yes, Breakthrough Listen is a 10-year search for extraterrestrial intelligence. It's the most comprehensive, sensitive, and intensive search that we've ever undertaken. And actually, just in a couple of weeks, on July 20th, we'll have our 5-year anniversary of the announcement of Breakthrough Listen, which marks the midpoint of the nominal 10-year duration of the program.
Any aliens?
No aliens as yet.
Okay.
But oftentimes we think about SETI as being very much a kind of binary activity. Either you find them or you don't. And if you don't have much to say. But we take a different approach in the Listen program as well as at the SETI Institute of late. And try to do a very good job of quantifying our null results, quantifying our limits that we place on extraterrestrial intelligence. And we think that that's very important for helping to kind of potentiate the field going forward so that other scientists, graduate students, postdocs know what we've done so that they can do better.
I think that SETI has really gotten this overhaul. I know back in the very beginning of the whole process, it was considered an interesting idea. Then it was considered an idea not worth investing any resources into, which is, I think, a big reason why the SETI Institute was able to go and raise a lot of its own money, or had to, and get some of its own access to its own radio telescopes. But it does feel now like it's gained a lot of legitimacy and doing a lot of fairly integrated research. Do you feel like we're in the golden age of SETI at this point, or entering?
Well, yeah, I'm not sure if it's the golden age.
Yeah.
Certainly it's a renaissance,
Yeah.
as others have said. There is a resurgence in the field. I think there are a lot of reasons for that. The history of SETI and SETI funding is complex. And involves termination of national funding in the 90s and a variety of stints of philanthropic funding. But I think the biggest reason why we're seeing such a surge in SETI is the results from the Kepler mission.
Mm-hmm.
The fact that we now know that exoplanets are incredibly common, that exoplanets are the rule rather than the exception. And from a kind of mediocrity principle, if we look at our own solar system, that seems kind of obvious in hindsight, maybe.
Yeah.
Like all sort of good ideas, it's obvious in hindsight. But it's important to recognize that 10 years ago, we didn't really know that with any certainty. It could have been that exoplanet systems were very uncommon, and that we were very unique. But of course, we now know that, at least in terms of the numbers of exoplanets and the numbers of relatively temperate exoplanets, that we're not unique.
And I mean, really, we've only known about planets existing since like 95, right? With PEG.
Yeah, 51 PEG. Of course, there were
PEG,
the pulsar planets as well, which as a
course,
radio
they don't
astronomer,
count.
I always have to bring up the pulsar planets.
Yeah. And so now we are starting to get a much better sense. And so it is kind of interesting the way you sort of lay that out. It's like all of these planets are getting discovered, and then the question is there life on any of them? And up until this point, that was a bad question to ask, and now suddenly that's a very important question to ask, and a lot of people are asking it, and suddenly people looking around going, is anyone checking? And the SETI Institute and others are going, we've been checking all along. Like, we're here, we're doing this work. It's very important. Welcome to this search. And I know that, for example, Breakthrough, that you have been publishing a lot of like bringing together all of the searches that have happened so far and putting it into some kind of single way that then people can do more comprehensive searches to look through it and find this information. What is the value of that for astronomers who are continuing forward on this?
Well, in any field of science, we have to climb the scientific ladder. We have to stand on the shoulders of those that came before us. And I think historically there was, I think, a reticence in astronomy broadly, not just in SETI, but I think SETI is a perfect example of this. A reticence towards publishing null results. And that makes it very difficult to know what stars have been searched over what ranges of wavelengths and in what manner. And we think that it's very important to get those null results into the literature so that people can do better experiments going forward. And in a lot of fields of astronomy, we always want to improve on what's been done in the past by a factor of 10. And that's readily possible in SETI, but difficult if you don't know what was done before. So how to do that. And so we absolutely do put extra effort into making sure that we publish all of our results. And of course, there's a certain level of analysis that you're forced to do on your data in order to subject it to peer review. That process of publishing a paper encourages a really close attention to detail in your work, and that's a good thing.
One of the things that I found really interesting is, I know there's a lot of conferences that are coming together, people who are, there's a lot of people that have like their main field. I think about people like, say, David Kipping, who's focusing on exoplanets, but is also into SETI and searching for technosignatures. And then you've got people like Jason Wright, who is focused on exoplanets, but also is doing a lot of really interesting work in exoplanets, in SETI. And it also really feels like there is where I would call it a golden age of SETI, is just the thinking of really clever ideas on how to recognize technosignatures, what are some clever ways that we could see alien civilizations interacting with their local environment. What are some of the ideas that you like right now best? Because the classic is we detect radio signals, but there's so many other ideas now.
Yeah, I think it's basically impossible to imagine all of the manifestations of extremely advanced technology. We, of course, have really no reason to believe that our current understanding of physics is in any way complete. And as we discover new physics, inevitably, we'll discover new manifestations of technology. As we develop new technology, we'll discover new manifestations of technology. And one of the very interesting areas of SETI now is Optical Seti, looking for laser pulses or looking for spectrally narrow continuous lasers. And that type of SETI really came about because of the invention of the laser. Charlie Towns and colleagues invented the laser, and very quickly after that made the suggestion that perhaps lasers could be used for interstellar communication, and that drives many of the optical SETI efforts. So I think what I find most interesting is that kind of conversation between our own technological development and our conception of extraterrestrial technologies. Another wonderful example of that is the Breakthrough Starshot program, which is a companion initiative to Breakthrough Listen, which is focused on figuring out how we could use directed energy propulsion to propel a small spacecraft, a gram-scale spacecraft, at some fair fraction of the speed of light. And as we start to think about propelling spacecraft in that manner, we start to ask the question, well, could we detect a directed energy system if it were in operation by another civilization? And that drives a particular new type of SETI search involving looking for transient signals rather than continuous signals. So I think that whole conversation is I think a very interesting one, and opening up all kinds of new directions in SETI.
But I mean, even just in the last couple of weeks, there's an announcement. I know that a couple of other researchers are going to be looking for evidence of solar panels on other worlds. Like, every time we develop a new technology on Earth, or every time we discover some kind of new type of physics, then suddenly we start to realize, oh, maybe we could search for chlorofluorocarbons, or a planet that's undergoing a greenhouse effect, or maybe we could detect transiting satellites, or and each time we develop technology, we see this thinking on that field. And so that almost does seem limitless. Each time we make a new technological advance, when we can somehow harness neutrinos, then suddenly we'll go, maybe we should be looking for neutrinos. Which of the techniques that are currently available is your favorite? Are you leaning towards the optical now?
Well, certainly, I like sort of the entire electromagnetic spectrum, and any speed of light information carrier is fair game. So neutrinos are quite interesting. Of course, gravitational radiation as well. Indeed, the signatures of our technology here on Earth are myriad. And if you're looking around at a city, there are buildings. That's a techno signature. Cars driving down the street, a techno signature. Indeed, pollutants from our factories, techno signatures. Artificial light from street lights. These are all techno signatures. But when you're thinking about trying to detect these techno signatures via remote sensing over vast distances, interstellar distances, you also have to couple your ideas of techno signatures with our observational capabilities. What can we actually look at? How much chlorofluorocarbon would need to be in the atmosphere of an extrasolar planet in order for us to be able to detect it with a telescope like JWST or LUVOIR or HABEX, one of these facilities. And so I think most of the time about what are the most readily detectable techno signatures. And the only techno signature that human beings have ever created that is readily detectable over distances spanning the entire Milky Way galaxy are radio signals, very bright radio signals like the planetary radar emitted by the Arecibo telescope, for example. So I think, of course, I'm a little biased because I'm a kind of radio astronomer by training, but I think radio still is a very interesting avenue to explore because these signals are so readily detectable with very little extrapolation from human technology. While I find extrapolating human technology to be very interesting, imagining what we might be able to do in 1,000 years or 10,000 years or 100,000 years, I think it's perilous because we really don't know what to expect. And I think if you asked someone 2,000 years ago or 5,000 years ago to predict what kind of techno signature we might have, I think you probably wouldn't find anybody who would predict planetary radar. Maybe you would, but
right.
So I think when I think about a good kind of SETI search, I try to limit the sort of extrapolation of our technological advancement.
There are some pretty amazing telescopes that are coming online, and I think as it relates to radio, there's the Square Kilometer Array, which I've heard would be capable of detecting Earth's air traffic control system at about 100 light years away. So up until this point, I've been always telling people, no, aliens aren't watching our television shows. They wouldn't be able to detect them. The signal would just fade away at those kinds of distances. But now suddenly we could detect just leaked radiation from other civilizations. How much of a game changer do you think that's going to be?
It's absolutely a game changer. So the very brightest radio signals that we have on Earth, the planetary radars, have pseudoluminosities, or a quantity called the equivalent isotropically radiated power of about 10 to the 12 watts. Then the next brightest class of transmitter is indeed the aircraft warning radars, the very powerful aircraft warning radars or missile warning radars. And those are about 3 orders of magnitude lower, so about sort of 10 to the 9 watts or so. And then the very brightest kind of isotropic transmitters that we have are about another 3 orders of magnitude below that, about 10 to the 6 watts or so. And actually those signals would be detectable with a square kilometer of collecting area from a handful of the nearby stars. And oftentimes, when we talk about things like the Arecibo planetary radar, a lot of communications engineers will make the point, which is very valid, which is the reason why that signal is so detectable is because it concentrates a megawatt or a few megawatts of power into a very narrow beam, which means it only illuminates a very small fraction of the sky. And if you sort of turn that around and you imagine that we're looking for something like that, we would have to be very lucky to be in the beam of a signal like that. And so the probability of detecting, an individual transmitter like the Arecibo planetary radar is very low, whereas the isotropic transmitters are going in all directions,
right.
So much easier to detect. And I think that's a really important qualitative step that we get to when we have approximately a square kilometer of collecting area, is that Earth's isotropic leakage starts to get in range. Again, only from a few very nearby stars, still very hard to detect. And we're not talking about decoding. We're only talking about detecting.
Right.
So you couldn't really watch the TV show.
Right.
You might know that there was
something's
channel
happening.
3 was at that frequency.
Yeah.
Which is would be enough, obviously, for a SETI search.
So let's assume that budget was no limit, and planet Earth wanted to get serious about detecting some kind of leak transmission, directed transmission in the radio, in the optical. What do you think would be the right machine to build? Would be the top priority to build?
Well, I'd say we go to the moon, the far side of the moon. Particularly in the radio, human radio technology, so-called anthropogenic radio frequency interference, is really a singular challenge. If it weren't for the fact that we were trying to do our experiments, our radio SETI experiments, immersed in a sea of human technology, it would be a relatively easy experiment to do. You would hook up your spectrometer to your radio telescope and you'd look for that spike standing up above the noise. But when you do that experiment from the Earth and you look for that spike, you see hundreds of thousands, millions of spikes all over the place, from cell phones and car radars and airplanes and satellites and all sorts of stuff. But there's one place fairly close to the Earth where you can get pretty far away from that and actually be shielded from it, which is for the moment on the far side of the moon. And of course, this is, the moon is a target of kind of renewed exploration by a variety of parties. And one of the things we've been thinking about in our group is how we might be able to do a SETI experiment from the moon. Incidentally, it gets you above the Earth's ionosphere as well, so you can observe very low frequencies that are impossible to observe from the surface of the Earth. It also gets you above the Earth's atmosphere. So forget radio, we can talk about terahertz radio, millimeter wave, mid-infrared, and access all of the wavelengths that are blocked from the surface of the Earth as well.
Yeah, so I mean, you would be able to detect the emissions from the first stars forming shortly after the Big Bang. You would detect the magnetospheres on planets orbiting other stars, and maybe you would be able to detect signals coming from aliens. All right, here's the easy question, which of course is the challenge of the Fermi paradox. This has puzzled everyone for a long time. What do you feel is the most realistic answer to the Fermi paradox?
Well, I think, can I have two? I'll just take my prerogative to have two.
Yeah.
I think a good answer, which is a common answer, is that we just really haven't looked much. I mean, in the grand scheme of things, in the 4.6 billion year history of the Earth, we've only had a technological capability that allows us to look for credible interstellar technosignatures for the last 50 or 100 years, which is just the blink of an eye. And so, even though we have done some SETI, and we're doing even better SETI experiments now than we were a few years ago, we've just really started looking. So that's one answer. Another answer is that I think that if there are such things in the universe as Kardashev Type 3 civilizations, galaxy spanning civilizations, and there's not something very strange that happens in terms of technological development, meaning that our kind of understanding of physics is kind of maybe not complete, but sort of complete-ish, let's say. If those civilizations exist, and what I said is true, then I think we probably have seen them, we just haven't recognized them. That there is some astronomical phenomena that we currently ascribe to natural, for lack of a better way of distinguishing between sort of technology and otherwise natural versus artificial, that we ascribe to some natural origin, but in fact has a very different origin.
And you actually fairly recently published a catalog of hundreds and hundreds of objects, any one of which could be that kind of object.
Indeed, yeah. One of the strategies that we are employing in LISTEN and also in our efforts at the SETI Institute is really to broaden our target list beyond just stars that are like the sun. Like the drunk person looking for their keys, underneath the streetlight. Initially, I think we thought we would look where we knew that intelligent life could arise. FGK stars, main sequence FGK stars, and much of SETI started there. In LISTEN, initially, we developed a nearby star sample that spanned a much larger range of spectral types, and we included in our program a component of it to look at so-called exotica, kind of interesting objects, things like Oumuamua, the first interstellar asteroid that we detected, or fast radio burst positions, for example. And the latest catalog that we published really attempts to bring some kind of systematic rigor to that exploration of the truly, truly unknown. And that catalog includes an example of prototypes, an example of every known object in the universe, a collection of superlatives, the most extreme, smallest stars, the brightest galaxies, etc., and also anomalies, just kind of strange things. And so it's a catalog of about 730, 740 or so objects, and we're working through that with our observational facilities.
Fantastic. Well, Andrew, please let us know when you do find the aliens. We would appreciate it. I'm sure Beth will tell us. But still, if Beth doesn't get around to it, definitely let us know. But absolute pleasure having you on the show with us, and good luck. We're huge fans of what you guys are all doing, and I'm so excited to see that SETI is getting a lot of support now and a lot of backing. So I think it's a serious effort worth looking for, and I really do hope you guys, even if you don't find aliens, there's going to be some really fascinating science that comes out of this.
Great. Well, thank you very much, and we're big fans of yours as well. So thanks for having me.
All right, take care.
Bye.
All right, let's move on to the news portion of the show. Beth, you're on my screen.
Thanks, Fraser.
Tell us about the picture that's behind you.
So the picture behind me is called Nihilus Fossae. And on one side of it, that side, I hate cameras.
I know, it's all reversed.
That side, I believe, is Jezero Crater, which is where Mars Perseverance is supposed to land. Today, the European Space Agency released some new data from Mars Express that should help the rover find some potential sampling targets, particularly in the search for life, which, being from SETI, of course, I'm very interested in. So it's Jezero Crater. Within this crater is actually a river delta. and the crater itself was once a lake. So they used Mars Express to map the rocks in the area, and they found two types of rocks. One is really olivine heavy, which is a magmatic system, and the other are carbonates. And the carbonates are what are fascinating to me, because carbonates tend to form on Earth in lake environments, and they're really good at preserving fossils. So in particular, alkaline lakes host stromatolites, which are layers upon layers of microbial mats. So they're some of the first signs of life we found on the planet, and you can still see a lot of them in Australia.
It's pretty interesting how, like, over time, I mean, they picked this as the location for Perseverance, and yet it just, over time, astronomers keep discovering more and more evidence that this is not only a pretty good spot, but like the best possible place to look for some kind of evidence of past life on Mars. Like, it just keeps doubling down as the better and better place. And so the stuff you talk about, I hadn't even heard about this stuff. This is brand new.
Yeah, this just came out today, so I'm really excited to be able to share it.
The kind of place you would find stromatolites, the kinds of places that you would find layers of ancient life. It just keeps getting better and better.
For me, it's fascinating because it's so hard. You look at Mars now, and these background pictures that Carolyn and I have, and it's dry and there's nothing there. So to imagine this giant lake behind me instead of a crater, is kind of fascinating. But when you really look at some of the more detailed pictures, the river delta is very clear. So there definitely was liquid water. It definitely was flowing into that crater. So that's really great. And if Perseverance can get to the spots around that river delta where those carbonates are and take samples, and then we have that potential for returning that sample someday. It would be wonderful to get that back, and maybe we could find some of those organic materials, organic molecules, stromatolites. That would be amazing. I would be floored. But it's so cool to me that we're like you said, we're getting ready to land there, we hope, and it's getting better every time we look at what we can potentially find.
And so what do those stromatolites look like here on Earth?
They, well, to the naked eye, they kind of just look like giant rocks. So if you were to look for them online, what you would see, particularly in Australia, they just look like big kind of boulders. But when you get closer and if you can kind of cut through them, they're just layers of these really thin microbial mats. So, but they're some of the oldest life that we found here, like billions of years.
Billions. Yeah, no,
billions
they're like
of years old.
3.8, I think. Yeah, 3.8 billion years old, or ish, here on Earth. They're so old.
Yeah, and so if you look back, they think that the lake in that crater was probably about 3.7 billion years ago. Yeah. So, there's definitely a possibility that could have raised to life at about the same time.
3.5 billion. Okay, 3.5 billion is the oldest I've been able to find. Oh, here's a great article on Universe Today. All right. Confirmed 3.5 billion years old. So there you go.
So yeah, so it's about the same time range. So that would be really cool to get some samples and maybe see if that could have developed there while it still had water.
Yeah. What does Curiosity have on board to be able to make any sense of this?
Perseverance.
Sorry, Perseverance. Yeah, not Curiosity. Curiosity can't see. Curiosity wouldn't see life if it was like crawling around it. But Perseverance.
Maybe if it was crawling around it. But,
okay, maybe so. Yeah.
Considering the pictures we've gotten, I'm not even sure about that. It's so basically it's designed to sample for life. So it's got a drill that can collect core samples. And it can also set some aside and cache them, basically, so that someday we can come and get them and bring them back. And it can test for oxygen producing in the atmosphere, subsurface water, so that kind of thing. It can characterize dust. It can do a bunch of things, but mainly one of the things it can do is set aside some of these samples, and hopefully we can go get them and bring them back and actually really do some analysis on them.
And it's funny, I mean, we're about to go on our hiatus, so before we return, Perseverance will have launched. July.
Yes.
And it's not going to be the only one. The Chinese are sending their Tianwen rover as well, which is going to be going. I think they just posted the launch date now between July 20th to 25th.
Wow.
So around
right now earlier than Perseverance is launching.
Right. Well, because Perseverance had a bit of a delay, right?
Yeah. So there's I think an issue with the packing, and so they've had to push it back another week.
Yeah. Very exciting. This is going to be, the launch is going to be pretty exciting. The arrival, it's going to be that whole thing. Remember back in 2012, we went through the whole 7 minutes of terror or whatever. It's going to be that all over again.
Yeah.
So,
and it's kind of a similar landing too. So it should be really.
Yeah. It's going to be the same. It's going to be the same thing all over again. I can't wait.
Yeah. I'm excited.
Yeah, totally. All right. Carolyn, what have you got for us?
Oh, I don't have anything as exciting as Mars. I have a really massive, supermassive, distant galaxy, a quasar way out in the distant universe called Poniuaena. Okay, I think I got that right. It's a Hawaiian language term. It means unseen spinning source of creation surrounded with brilliance, which pretty much describes a quasar.
Yeah, that's amazing.
So the existence of it is spurring a lot of questions, and it's very distant. It's about 13 billion light years away, which puts it at a time when the universe was going through what we call the Epoch of Reorganization. And that's a time about 400 million years after the Big Bang, when the universe was lighting up and had first stars and galaxies are forming. And astronomers have been probing this epoch of history to kind of understand what's been happening with the very earliest stars. And they're seeing these massive stars. I think HST got an image of a very massive star, and these shreds of galaxies that we know will then combine to make larger galaxies later. And they're finding these really distant quasars. And to do this, they have to use very sensitive telescopes. So they have the Gemini telescopes, the Keck telescopes. They, in fact, use those two to look at Poniuaena. And among other things, figured out that this thing has a supermassive black hole that has the mass of about 1.5 billion suns. Okay, this is big. And it's apparently a very voracious eater. So I was on Twitter earlier today, and I saw that Phil Plait was writing about it. He had this whole Twitter stream going on.
Yeah.
And he calculated that this thing eats about the equivalent mass of 4 Earths per second.
He was saying it's eating the solar system every day.
Pretty much, yeah. So, and I want to thank Phil. He did the math, so I didn't have to. But anyway, so to compare this, the most distant quasar that we do know is called ULAS J1. I had to read this 1342 plus 0092. It doesn't have a fancy name.
Yeah, quasars
and
need better names.
It lies just slightly farther away. Yeah, we need a better name.
Yeah.
So it's 13.1 billion light years away, and so it's a little bit farther away than Poniuaena. So its supermassive black hole has the mass of 800 million suns. So there's a pattern going on here that you can see. We only have 2 examples, but there's a pattern of these incredibly massive galaxies, supermassive black holes at the center, powering these quasars. And that's piling up a lot of questions, which we don't have answers for yet.
Yeah.
So one of them is, it takes a long time to make these galaxies. It takes a really long time to make a supermassive black hole like these. So for a quasar like Poniuaena or ULAS to do this, to exist, when the first stars basically are still really forming, the first galaxies, raises a lot of questions about how did this engine grow so fast? What's going on here? And I don't think there's really an answer for that yet, but it's one of these kind of fundamental mysteries of the Epoch of Reorganization.
Yeah, I mean the idea being that there's only so fast that a black hole can consume material. And you can make it happen a little faster if you start if supermassive black holes are forming separately and then they're smashing together, and then that's a fast way to sort of distribute the work. Many hands make light work in this case, but still, it just seems each time they find one of these quasars earlier and earlier in the universe, it's just shocking how busy they've been already. The universe is merely 700 million years old, and
it's like a baby.
It's a baby, and already these black holes have gobbled up hundreds of millions, sometimes even billions.
There's a lot of material there. I mean, there's all the primordial hydrogen and everything.
Yeah.
And then if there's, I would guess if there's, I'm sort of extrapolating here, I guess if there are a lot of really supermassive stars exploding and seeding the universe. You've got more stuff there to feed these. And so the big question now is, okay, we need to find earlier quasars if they are there, to kind of set a limit on, okay, maybe when do they really start to form? Because I'm not sure that that's even very clear yet. And then figure out what's the mechanism that's causing these black holes to, you know, really coalesce this fast and to exist so early in cosmic history.
Yeah. I would. Do you know sort of where this search is? See, I hadn't even heard the name. Is it? It's interesting that they gave this quasar specifically a name. Is it because of its distance, because of its activity? Do you know why it was singled out and given a name?
Yeah, they didn't really say, and I probably should write and ask. I mean, they're using Keck and Gemini, and there's been a concerted effort to start to use more native names.
Yeah.
For various reasons.
Makes
I don't
a ton
know
of sense,
you know, why there is. But there are people on the Big Island. There's one or two people that are really expert at coming up with these names that are native. And so they've been doing this. And I think it's really pretty cool. I mean, we have Maki Maki and, you know, Oumuamua and things like that I think are just really cool names. And so now we have Poniuaina, and I'd kind of like to see if they could rename Ulas, J1842. Rename that one to a really cool name too.
Yeah. Awesome. Thank you, Carolyn.
Sure.
Michael.
Yes. So before I get started, I did want to show off this little thing here. It's called the Mini Museum. I don't know if you guys have heard of this, but it's got like a bunch of cool little stuff in it. And one of them is the earliest life there. That's one of those things from Australia that you were talking about.
Yeah.
So there's these cool little things.
That is seriously cool.
I don't know if you can see. I've got two of them here.
Nice.
Yeah.
It was a Kickstarter project. They've come out with, I think, 4 versions total now.
Not sure which ones I have. Hold on. I've got here. So I've got Oldest River. I've got I've got the asteroid belt. I've got Mammoth Meat. I've got Petrified Lightning. Samurai Sword. I've got a chunk of Samurai Sword there.
Well, I'm gonna have to get one of these too, so I'm not left out.
Yeah,
I know.
My wife picked them up for me during that Kickstarter, and they're definitely some of my most prized possessions.
Yeah. The only reason I got this is because there's a little piece of Apollo 11 foil in there. It's like, I got it. I don't care how much this is. I'm gonna buy it.
That's cool. Let me just check again. I don't know if I have that one. But what's your news, man?
Let's talk about astronomy news. Right?
I have a chunk of the Enigma machine. I have the chunk of the World War II Enigma machine in mine.
Very cool.
First supercomputer. Please.
All right, so
all right, we're distracted here. They're called mini museums if you want to check these out.
Yeah. So we think we know why Betelgeuse was dimming. So one of the popular ideas, there was kind of 3 main ideas. The most exotic one was that, you know, this thing was about to blow up and we're seeing the early stages of a supernova. It's still around, it hasn't blown up, so that wasn't it. Another idea was that there was a lot of dust in the atmosphere. So when stars get very old, they start to pulsate and their atmospheres really stretch out. And so the farther away you get from a star, the less its gravity is going to be. So this material that's being kind of pushed out from the star can escape, it can cool down, and in the process it forms dust. And dust is kind of this all-encompassing term. Astronomers, we don't really know what it is. We know that it's silicates, maybe. We know it blocks light, and it's kind of it can be like a catch-all solution for many things. But it seemed reasonable that dust was the cause for this. So there were further observations that were done, specifically looking in the sub-millimeter wavelength. So this is longer wavelengths past infrared, not quite to radio yet. And the idea is that if there was a lot of dust, that the dust should be bright in these wavelengths. And so they looked at Betelgeuse in these wavelengths. They didn't see any sharp emission, and in fact, what they saw was that the brightness at these wavelengths was actually going down as well, along with, you know, every other wavelength. And they're able to tie this to the photosphere of the star. So essentially what they're saying is that the sub-millimeter wavelengths that they're looking at that light is emitted from the surface of the photosphere of the star, which means that the temperature should have decreased. And one way to do that, really the most likely way, is you just have a really giant sunspot or star spot. So what we think then is that Betelgeuse just had a really massive star spot that covered about 50% of the surface. And in fact, if you look at the images that were taken, the high resolution images of the surface of Betelgeuse, you did see these giant dark patches.
Yeah.
And we think that those then were these star spots.
And this is something that I think people don't realize, that the size of the star spots on Betelgeuse can be 60% the size of Betelgeuse. Not 60% the size of the sun, but 60% the size of Betelgeuse. So on the sun, star spots are relatively small, the size of, merely the size of the Earth, or bigger. But just imagine when Betelgeuse is taking up the orbit of Mars, and these star spots are hundreds of millions of kilometers across.
It's terrifying.
Every part of Betelgeuse is terrifying. Just blow up already, and just stop freaking us out and just be done with it. Yeah. So why I guess does this seem to be the most likely cause now and not the dust? Why do they like this?
Well, a lot of it is this fact that the submillimeter emission is tied to the photosphere of the star. So if that is the case, then it has to be that the surface of that star is changing its properties, and it should be then that the temperature is just decreasing, because the brightness of any thermally emitting object is tied to its temperature. And so if the brightness goes down, then it should be that the temperature is going down. And they ran some models where they did throw in some dust into the model, into their simulation, and they saw that even with dust added into the atmosphere, it didn't really affect the emission at these longer wavelengths very much. And that's kind of something that we know, that you've got these objects called submillimeter type galaxies. You can see really far back in the ancient universe, and they're somewhat impervious to dust, meaning that light at these wavelengths can penetrate through the dust and we can see them. So dust then really shouldn't affect that emission there.
Is there a way that we can know for sure? Like, I'm assuming the star is rotating, and would there be a way to time it, or do the features change? Like, would you see it? Like, sometimes, like, we can observe the sun, we can see some kind of sunspot complex. It rotates around the back of the sun, and then it comes back around the front, and so you can sort of see this periodic dimming of the sunspot. I wonder how quickly Betelgeuse is turning, or if these sunspots change in size, because I mean the star is so big, so it's not like it's going to be turning. If it turned fairly quickly, parts of it would be moving at close to the speed of light, right? So it's got to take a long time to turn, and so I wonder which is a faster activity.
That's a really good question.
Thank you.
I do not know the answer to that.
No problem.
That's, as astronomers would say, that requires more observations to be able to answer that.
I wonder if they can even tell how quickly it's rotating, because it would be tricky. I mean, a lot of times with stars, you do need to look at sunspots, but I guess it's maybe too far away to be able to really determine. Absolutely fascinating. All right, well, before we wrap this up, I just wanted to bring up one really interesting story that I would hope that someone would grab. Nobody had, so I'll just quickly talk about this, and which is astronomers were observing a dwarf galaxy about 75 million light years away between the year 2001 and 2011, and in comparing the pictures between those 2 years, they discovered that one of the stars they were looking at was just gone. And it was a fairly massive star, one that was giving off the kind of radiation that would have made it the kind of star that would detonate as a supernova. And they initially thought, okay, well, so it's probably some kind of dust, because it's always dust passing in front of it. But another theory is that this is a kind of supernova. There's a term that I've heard, they didn't use it in this one, but it's called an unnova. And the idea is you have this star as it reaches the end of its life, and the core of the star builds up these various layers, and you've got iron at the middle of the star, and then the stops producing fusion at the core of the star because there's no energy released when iron is fused together. And so then it causes this core collapse. All of the outer layers collapse in on themselves. And what we normally see with these supernovae is they then bounce off of the center of the star, and then you get this really bright explosion, and then you get this black hole. But one of the other theories that you can get is that maybe these stars collapse in on themselves and they don't bounce. The black hole is able to handle all of the matter that's falling in at like 70% the speed of light. And so the star just disappears into a black hole. And they think that either dust passed in front of this star, or they watched one of these unnovas happen, that a very massive star just disappeared, just turned into a black hole, all gone. And if that's the case, then it might very well be that more of these supernovae or more of these really massive stars that you would think would be exploding as supernovae are just disappearing. And we won't be able to really know for certain until we can get gravitational wave sensitivity up to the point that you could actually detect the ripples in space-time as this very dramatic event is happening and you've got the birth of this new star. The only way you could see it would be in the realm of gravitational waves. So absolutely fascinating, and could be an entirely new kind of detection if this works out. So I'm pretty excited about it. All right, well, we've reached the end of our show. Michael, you're on my screen right now, so why don't you let us know what you're working on and where people can follow you over this whole summer.
So I'm on Twitter at Michael Roderick. We just had a successful Astronomy on Tap virtual session on Monday. So we'll be back in July. We don't have a date or topic yet. But if you look at my Twitter, you'll be able to find out once we post that event. On a more personal note, I finally bottled my first batch of mead.
Oh, great.
It's absolutely awful.
Oh,
so
good.
I'm hoping that over time it will age in those bottles, and maybe in a year or so we can try it again.
Is it supposed to be awful when you first make it? I mean, some alcoholic beverages taste terrible and some taste good as soon as you make them.
Yeah, they say a lot of the stuff kind of mellows out after you age it for a while.
Yeah.
This is my very first one, so
Yeah.
100% I thought myself.
I've heard that it can get contaminated super easily, that the honey can get wrecked, that you got to be really, really careful.
Yeah.
Well, congratulations, and this is the process. This is science. Come on, you're used to this.
Trial and error.
Carolyn, what are you up to?
Making masks. A lot of masks made out of spacey material.
Oh, that's cool.
And selling them and having a good time. Also working up some podcasts based on some sections from one of my books. So I'm hoping to work on that this summer, and otherwise kind of writing out the pandemic like everybody else.
Yeah. Yeah, you guys have it pretty rough there in the US. If people want to follow what you're working on, where can they go?
Yeah, I have a webpage called thespacewriter.com, which will take you to my blog. And I'm also on Twitter at spacewriter.
Fantastic. Beth?
So in celebration of the landing, the Art Imaginarium just announced that our challenge for July is actually doing Jezero Crater as it was in the distant past. So I'm looking forward to seeing all of the artwork that our members are going to give us. And so if you're interested in coming and playing and doing the artwork, go to the SETI's website and we'll have information on how to join that group.
Terrific. And if people want to follow the work that you do, where do they go?
Just follow me on Twitter at PlanetaryPan.
Fantastic. All right. And of course, all of the shows have gone on hiatus. Open Space, Virtual Star Party, Astronomy Cast, now the Weekly Space Hangout. This is the final show that we are going to turn out the lights and say goodnight to. We will be back in 2 months. I'm going to be very busy on all of the other projects, my weekly newsletter, the Guide to Space that I do on my YouTube channel. We're going to be doing a lot of really interesting experiments with live streaming telescopes as we try to figure out better methods for the next season. So not going anywhere. I'm just not going to be finding high-speed internet every week. But you should definitely make sure that you follow all of the people, and definitely don't forget, join the Weekly Space Hangout crew, and they will help you get through this summer of space. All right, I'm going to bring everybody back here on my screen.
Fraser, are you participating in the CosmoQuesticon?
Yes. Yes, of course. Pamela has, I don't know what I'm doing. I think Pamela has just said, make yourself available for the CosmoQuesticon. If people don't know what that is, do you want to let people know what it is?
CosmoQuesticon is a virtual event we're doing for about 2.5 days, July 17th through the 19th. I'm pretty sure Nancy will share the information in channel, and it's basically a science fiction / science / creative con, all held on Discord and Twitch.
Perfect. All right. Arjun says, I want you fluent in Chinese when we all get back. Okay, you got it. I'm working on it. All right. Thank you, everybody, for joining us this week. A lot of fun. Thank you for everybody joining us this entire season. Thanks to all the mods. Thanks to everyone in the Weekly Space Hangout crew for leading the show, telling us what to do. And we will see all of you in 2 months. Thanks, everybody.
Bye, everybody.
Bye.
But